Is my screen visible?
Yes, sir.
Thank you. We have studied construction of synthesis of Mealy machines as well as Moore machines. Both are representations of the finite state machine. Both are implementation, I mean kind of implementation of the finite state machine. And both of them have the same expressive power. So whatever can be realized using a Moore machine can also be realized using a Mealy machine. So what this means is that you can convert a Moore machine into an equivalent Mealy machine and vice versa. So first let us see how to convert a Moore machine to a Mealy machine. So as I said before, that neither are more powerful than the other, but the number of states that you need in a Moore machine is usually more than what you need in a Mealy machine. On the other hand, the logic you need to implement a Mealy machine is often more complex than the logic you need to implement a Moore machine. So depending on the situation, depending on how much memory you can use or how much circuit you can use, you choose one of the following. But to be honest, in a synchronous circuit, in a synchronous sequential circuit, there is not much to choose between them. So any whatever is natural, whatever the designer comes up with as a choice can be used. Okay, but nevertheless we study that how to convert one to the other. But let me tell you, in the case of asynchronous systems where the transition is not at the clock but can be at other times also, then depending on the situation, sometimes one of these machines have advantage over the other. So in some situation Moore machine is better, whereas in some situation the Mealy machine is better. There is one more difference that I would like to point out is in the delay. So as we discussed previously, in the Mealy machine, the output signal is only comes after the clock. It is only transiently in exchange with the input. It comes, so it comes along with the input. But whereas in a Moore machine, the output signal is continuous. It's there. So this causes a small delay depending on the width of the rising edge. So this should also be adjusted for. In the synchronous machine, this is not really a problem, but in asynchronous machine, sometimes this is a problem. This is a difference. Okay, so let us see. So as you know, the difference between a Moore machine and a Mealy machine is that in the Mealy machine, the output is a function of both the current present state and the input, whereas in a Moore machine, it's a function of only the input. So the output function is from sigma cross delta to sigma. No, sigma cross delta. Let me. Yeah, it is q cross sigma to q for the transition, and for the Moore machine, the output lambda is only q to delta. The sigma is not there. The input is not there. Whereas in a Mealy machine, the output function lambda is q cross sigma to delta. So that's the only difference. So you would have in a Mealy machine, cross sigma to delta. This is the output function. But this can easily be handled. for the purpose of conversion. What you should do is that, so you are converting a Moore machine to Mealy machine. Let's say lambda is the output function for the Moore machine. And delta is the transition function for the Moore machine. In the equivalent Mealy machine, everything else remains the same. So delta Mealy would be same as delta Moore. The only change would be in the lambda Mealy and lambda Moore. Okay. So lambda Mealy, the output that you produce at state Q and input A, is lambda Moore applied on delta Moore. So what you do, if you have a state input pair QA, you first apply the state transition, move to the next state using delta Moore, you move to the next state using the delta Moore, and just because lambda Moore is a function of only the state, so for the next state, on the next state you apply lambda Moore. Whatever you get, that is same as lambda Mealy. So this is just stating, this is just doing this thing. This is just doing this thing. You are going to the next state and then applying, computing the output, finding the output. Okay, you come here. So you are here and you have an input of 1. What in a Moore machine? So what you do is that you first move to the next state, and then using a Moore machine you find out the output. And this would be equivalent to this action. This is very simple to illustrate in terms of the state transition diagram. Okay, in terms of the state transition diagram. So let's say this in the top, what we have, this is my Moore machine. This is my Moore machine. And I want to convert it to an equivalent Mealy machine. Okay, so in Moore machine, you know, the output is associated with the states. The edges do not have any output associated with them. They have only the inputs associated with them. Whereas in the Mealy machine, the outputs are associated not with the states, with edges. So the output is on input in Mealy machine and the output is on state in the Moore machine. So it's pretty easy. I think you have already figured it out. So what you do is that, so if this is the output for a particular state, in all the edges leading to that state, you copy C. Okay, so in all the edges that you have, you copy C. So C comes here, that's the only edge, and this C gets copied here. This gets copied here. Similarly, A would be copied here. Similarly, C would be copied here. Okay, so all this will be copied. All this will be copied. Similarly, here this C will be copied. So you take basically you take the output of a state, and for all the incoming edges to that state, you copy the output. and remove the output from the state. Okay, you see that's what we have done, and you get the equivalent Mealy machine. All right. So what happens in terms of the transition? So let's take a more the state transition table. So this is clear. Graphically, it is clear. You take the output of any state, take it out from there, and in what are all the incoming edges to that state, put the output in those edges. Take it out from the state, put in all the incoming edges, and you get the equivalent Mealy machine. The states are the same. States do not change. You have same set of states in a Moore machine and the equivalent Mealy machine. So let's see what happens in terms of the transition table. How does the transition table of the equivalent? So I am taking a transition table of a Moore machine, and I will try to say that what is the transition table of an equivalent Mealy machine. So this is one transition table for deciding even number of zeros and odd number of ones, or accepting even number of zeros and odd number of ones. So this is the transition table. Note that because since it is a Moore machine, I do not have output for every input. So this implicitly means that this is 0 and this is also 0. This implicitly means that this is 0 and this is also 0. This is 1 and this is 1. This is 0 and this is 0. For both input, I have the same output. So all I need to do is to just delete this. Just delete this, and this is my equivalent Moore machine, Mealy machine's transition table. This is my equivalent Mealy machine's transition table. Okay, pretty simple. Okay, so now let us look at the other way around. So that means you have a Mealy machine, you have to convert to a Moore machine. So in this case, what happens is that the number you see, I have already told you that from conversion of a Moore machine to a Mealy machine, the number of states are the same. They remain unchanged. The number of states remain unchanged, and they are identical. States remain unchanged. States remain unchanged. But when you are converting to a Mealy machine to a Moore machine, you have to increase the number of states. Okay, so let's see how we go about that. Let's see how we go about that. Okay, so my starting point is this. My starting point is this Mealy machine. Looking like a Greek alphabet. Its starting point is this Mealy machine, and I want to get to this Moore machine. Now it looks like the Roman alphabet. Okay, so let's see what happens. So see, so in the conversion process, what should really happen is that this output should not come with come on the inputs. It should rather come with the states. Okay, let's see what happens. Let's try to do the following. Let's try to move this from here to here. Let's try to move this from here to here. So what happens on this transition? On this transition, what happens is that from Q0, on receiving an input 1, on receiving an input 0, I stay in Q0. On receiving an input 1, I move to Q1. And what this edge says in the Mealy machine is that you should output 1. So I move to Q1, let's say I output 1. Let's say I output 1. I move to Q1 and output 1. But now what this means is that since it is a equivalent Moore machine, the output is tied with the state. So that means whenever I am in Q1, I should always output 1. I should always output 1. Whenever I am in Q1, I should always output 1. That's fine for this edge. That complies to this edge. I am in Q0, I get an input 1, I move to Q1, and I output 1. That's what this edge says. That's what this edge says. But now let us look at this edge, this self loop edge. Let us look at this edge. So I am in Q1. I received an input 1. I am still in I'm back to Q1. I'm in Q1 again. But now I should output a 0 according to this edge in the Mealy machine. I should output a 0. But I have already told that whenever I am in Q1, I should output 1. So this is a violation. This is not complying to this edge. So what's the solution? The solution is that you split Q1 into 2 states. You split Q1 into 2 states. So this is another state, and this is the old state. And instead of, what are the 2 states? First state is, the state is Q1 and the output is 1. And the next state is Q1 again, but the output is 0. Okay. So if you have 3 possible outputs that could have come when you are transitioning to Q1, it would split to 3 states. It would split to 3 states. It would be Q1, 1, Q1, 0, or maybe if there are 4 states, say 0, 0, 1, 0, 1, 1, 0, 1, 1, it would be Q1, 0, 0, Q1, 0, 1, Q1, 1, 0, Q1, 1, 1. It would split to 4 states. So Q1 would split to 4 states. If so see, the same problem is not there for Q0, because the only way I am coming back to Q0 is from itself, and I am outputting 0. So if I just put 0 here, that would do. That would do. I need not split into Q0 0 and Q0 1, because the only output that I get in Q0, only way I am in Q0, if you don't take into account the start, only way I am in Q0 is when I am in Q0 and I am getting an input of 0, and the output in that case is 0. There is no other case. So Q0 need not be split, but Q1 has to be split. Q1 has to be split. Because there are 2 possible outputs you can get staying at Q1, depending on how you have reached Q1. How you have reached Q1. And you can have 2 different outputs. So I have a state for each of them. So that's what I have done here. That's what I have done here. I have Q0 I have written. I mean, just to maintain the same terminology, even though just Q0 would have sufficed, but just to keep and tally with the rest of the things, I have written Q0, Q0, 0. And you see in the output is 0. That's what this says. The output is 0 when I'm in Q0. Fine. Q1 I have split into 2 states. It is Q1 1 and Q1 0. I have split into 2 states. Naturally, by definition, by my design, whenever I am in Q1, 1, my output is 1. That's how it is defined. Whenever I am in Q1, 0, my output is 0. That's what is defined. Okay. So now let's see how the edges change. So you look at an edge. If it goes to Q1, fine. So it goes from Q0 to Q1. So it starts from Q0, it goes to Q1. So it could have either gone to this, or it would have gone to this, because the Q1 state has now split into 2 states. It could, this edge could have either be here or here. But since the output is 1 on this transition, it should be here. Now look at this edge. So it starts from Q1. So it can start from either this or this, and it ends in Q1 again, but with output of 0. So this should end here. This should end here, and then that means it should start from it should start from here because it's an input 1. But now you see there are two things possible. So it can start from either Q11 or it can start from Q10. So this edge also, because this is a self loop on this state, and this state has split into two. So this self loop will now break into two edges. One is a self loop from Q10 to itself, Q10 to itself. Another is a edge from Q11 to Q10. Another is a edge from Q11 to. So this edge has split up into this edge and this edge. Similarly, let us look at this edge. It's again a self loop. On receiving 0, it produces an output 1. So this again splits up into. By the way, here see it is an input 1. So both of these are an input 1. Both of these are an input 1. Now let us look at this self loop. This self loop. It is again split up into two. It is from Q1 to Q1 itself. So now there will be two loops from Q11 to Q11 and from Q10 to Q11. And can you understand why it is from the self loop from Q11 to 11 and Q11 to, because see the output is 1. So this edge, when it splits up, the destination of this edge should be Q11 because its output is 1. Because its output is 1, this edge now splits up into this and this, and both have destination Q11. Both have destination Q11. Input is 0 and so on. Okay, so let's see what has actually happened. What has actually happened is that the state Q1 has split up into two states. One is Q1 with the output of 1, another is Q1 with the output of 0. The edges which lead into Q1 will now also be split, or which start from Q1 will also be split. Now, so each of the self loop, there are two edges which end in Q1. Two edges. Yeah, this edge is already taken care of. So there are two remaining edges which are ending Q1. They also split into, each edge split into two different edges. Okay, and depending on what the output on each of these edges, the destination node of each of these edges is determined. Let's take another example. This is a serial adder. This is a serial adder. By the way, I'll soon explain what this actually means for the state transition table. This operations mean for the state transition table. Okay, let's see. So this is a serial adder starting from LSB. So this we have already defined the Moore machine here. Is it? No. Anyway, missing it somehow. Anyway, so this is a serial adder starting from LSB, and this is the in the left hand side you see the Mealy machine, the pink one. I'm not explaining why it is like this. You know that I told you that you have to remember the number of the index, the parity of the index. So that way I'm not doing it. So okay, maybe let me quickly tell. So there are two inputs, X and Y. Every bit of two inputs, X and Y, and depending on when the carry gets, you get, so you have two outputs again, carry and sum. Depending on when the carry gets, there is a transition. You have to look at the position where there is a transition, and from that you move to a new state. Okay, so let's assume that this is the Mealy machine. It is already discussed in the class. So let's see how Q naught behaves. See, now Q naught, let's look at the incoming edges to Q naught. So Q naught has one self loop where output is 1, 0. So let's see what are the possible outputs that one can have when one transitions to Q naught. You can have 1, 0. You can have 1, 0 again. You can have 0, 0, and you can have 1, 0. So there are two possibilities: 1, 0 and 0, 0. I'll explain. So let me, in the equivalent Moore machine, I'll explain this a little bit later. Let's look at this. Forget about the start state. Let's look at the other two. So Q naught, because there are two outputs possible when you transition to Q naught, one is 0, 0 and one is 1, 0, 0, 0 and 1, 0. So I have split it into two states: Q naught 0, 0 and Q naught 1, 0. Similarly, symmetrically, if you look at Q1, you see that there are two outputs possible. One is 0, 1. And the other is 1, 1. Okay, so Q1 also I split into two states: Q1, 0, 1 and Q1, 1, 1. Q1, 1, 1. Okay, so how I create the state? See, at every state of the Mealy machine, I look at what are the, if that is the next state, what are the possible outputs that can happen. For each possible different output, we have a separate split state. So if there are 3 possible outputs or 4 possible outputs, so the corresponding state, let's say Q1 here, will split into 4 states if there are 4 possible outputs. It will split into 2 states if there are 2 possible outputs. Okay. So now let us look at, see what happened to the edges. So this thing I'll explain a little bit later. Okay, so let's look at this edge. So I am in Q naught. On receiving an input 1, 0, I transition to Q naught again and produce an output 1, 0. So can anybody tell me what are the edges that correspond? Who is this particular? Let me give a color. Anyway, what are the edges that is split to? So it produces, see, this edge produces an output of 1, 0. Produces an output of 1, 0. So it should, this edge should have a next state whose output is 1, 0. So this should be this. Its next state should be this, because it is corresponding to output of 1, 0. And then it produces an output of 1, 0. That's fine. Now, what are the split things? See, it starts from Q naught. It will split into two edges. One is this one. It starts from Q naught 1, 0 itself, receives an input 1, 0, and then comes back here. So one of these edges. So there are two edges here actually. It's there. What are the other thing? So this will split into one of, so this is 2 copies actually. So one of these. Okay. What about the other one? What about the other one? Which else? See, the another is this one. It receives an input 1, 0. receives an input 1 0. Yeah, so the other is one of these edges. Okay, so this way the edges, so it's very easy to decide. You just find out what is the destination state, what is the next state from there, and you draw an edge from the previous state to that, present state to that. Okay, similarly you can complete. So this I'm coming back. What is this O epsilon? So let me tell the rule that. So by the way, what happens in if we look at the state transition table, let me tell you what happens. Let me write it down this way. So this is my Mealy machine that I'm drawing. So you have Q0 and Q1 on input 0. Q0 stays in Q0 and produces an output of 0. This is input, this is output. This is input equal to 0. So this is input, this is output. This is input equal to 1. Q0 0. On receiving an input of 1, it goes to Q1 and produces an output of 1. When I'm in Q1, on receiving an input 0, it's back to Q1 and produces an output of 1. Similarly, on receiving an input 1, it's back to Q0 and produces an output of 0. Okay, so this is the equivalent Mealy machine. So sorry, this is the Mealy machine. So what will happen in the equivalent Moore machine? You see the number of states will increase. So in terms of the transition diagram, what is there what is the special about Moore machine is that this output, for if you look at a particular row, this should be same for all the inputs. For all the inputs, this is not a Moore machine because the output is different here. Output is different here. Okay, it should be the same. So how do we achieve that? We increase the number of input states. Increase the number of input states. You write Q00, Q11, Q10, and this is the next state. Input equal to 0 and input equal to 1. I'm just writing the output, but we'll let us see that you can move out the output. Okay, so come Q00 on receiving an input of 0, it is back to Q00, produces an output of 0. On Q00 and receiving an input 1, it goes to Q11 and produces an output of. It goes to Q11 and produces an output of 1. On Q11, on receiving an input 0, it's back to Q11 and produces an output of 1. And on Q11 input of 1, it goes to Q10 and produces an output of 0. Okay. No, sorry, I think I have stated you wrongly. These outputs will not be the same. If you are in the same state, so if we look at the next state to be Q0, wherever there is Q0, the output should be same. It's not that in a row all the columns has to be same. Whenever the output next state is Q naught, your output should be the same. So let's see that property is maintained here or not. So I am in Q1 1, Q1 0. I receive an input of 0. I am in Q1 1 and produce an output of 1. I am in Q1 0 and I receive an input of 1. I am in Q1 0 and produce an output of 0. Now let's see. So Q0 0 output is 0. Anywhere else Q0 0? No. Q1 1 output is 1. Q1 1 output is 1. Q1 1 output is 1. So whenever the next state is Q1 1, the output remains the same. Okay, which means it is a mode machine. So whenever the next state is same, the output is also the same. Okay, so that's what we have achieved here by this. So let's summarize the rules from Mealy machine to Moore machine conversion. In the Mealy machine, let a state Si have input transitions, different input transitions with the different outputs OJ1, OJ2 up to OJI. These are the different outputs that you can have on transitions from Si. In the Moore machine, you create equivalent Moore machine, you create new states, as I told before, Si J1, Si J2 up to Si Gi. You create new states. And naturally, the output in each of these states will be OJ1, OJ2, and OJI. If there is a transition from Si to Sj on input A with output OK, create a transition from each copy of Si to Sj. So if you have a transition with output OK from Si to Sj, so you look at, so it's like this. So if you have Si, you have Sj. Okay, and so now Sj might have different copies because of this process. Sj might have different copies. Let one of the copy be Sjk, which means that there is an output. So let me talk about the original Mealy machine. So Si to Sj, I am transitioning on input A and producing an output OK. Producing an output OK. So basically it's OK. Okay. So what I do, if it is A OK, look at Xjk. Similarly, there are multiple copies of Si which it has been split into, let's say Si1, Si2 up to say SIL. So, and this is Sjk. From each of these, there will be an edge. So this one edge will be converted to these multiple edges. To these multiple edges, they'll be converted. They'll be, so from so the input from all split edges of the input, and if it is OK, only Sjk. From each of these, there will be edges. So this edge will get converted to this. All right. So now let's come about that start state. So in the Moore machine, let O sigma be a special symbol which is output at the beginning when no input is received. So the delta Moore is basically delta Mealy plus this extra O epsilon. Is the extra symbol that is output. So what you do is that when you are splitting the start state, in addition to the splits based on the outputs, you also create a new state, which is Q naught prime and with an output of O epsilon. Okay, so as in here. So you split, this is your start state is Q naught. You split your Q naught into, based on your output, you split into 2 copies. But you also create an additional, a new state because of this kind of dummy output, O epsilon. So the outputs earlier were 0, 0 and 1, 0. You add one more to delta, it's this O epsilon. So you add this O epsilon to, so the output is O epsilon 0, 0, 0 and 1, 0. Okay, so this is basically delta Q naught. Outputs possible from Q naught. Now, since this is an additional output, you should also have an additional state created for this. That's what has been created, Qi O epsilon. Okay, and successors of this new state are same as those of any copy of Q naught. So you take any copy of Q naught. So for all copies of Q naught, if Q naught is split, whatever outgoing successors you have, same successors will be there for Q naught prime also. Okay, same successor of Q naught will be added to the start set also. This, you need not do all this if the start state is not split. If the start state is not split in this conversion process, then you need not do all these things. Okay, so the reason this is done is basically to, because you see how I'm splitting the state. I'm splitting the state based on the outputs that I can have. But initially I don't have any output. So that's why this kind of dummy output O epsilon is created. Okay, so I think with this we end. Just to summarize again the process of synthesizing a synchronous circuit. From the problem, create a state diagram or a state table. The step 2 we'll do in the next class is to do a minimization, and then select a set of state encoding and the type of memory elements, D flip-flop or JK flip-flop, or how many memory element. Based on this encoding, derive the transition and the output table, and depending on what type of flip-flop you are using in memory, create an excitation table from the transition table. So if it's D flip-flop, it's the excitation table is simple, otherwise it is more complex, depending on SR input and the corresponding output that should be there. And now you have the Carnot map, the transition table and the output table, or rather the excitation table itself can be thought of as a Carnot map. Minimize it, find out the realization, draw the circuit diagram. So these are the steps you should follow. So following these steps, we have an assignment in the lab for you. The conversion from to the BCD, the double algorithm. It's already there in WBCM. You can look up WBCM, there it's described. You have to go through these steps and design the circuit, a sequential synchronous circuit, to realize the algorithm. Okay, thank you. So in the next class in Monday, we'll discuss about minimization. Just like we minimized combinational circuits, we will minimize sequential circuits also. Thank you.